Hi, I completed my OneTesla kit assembly and I'm excited to try it together. Let's dim the lights. You should always keep a proper distance from Tesla coil. Let's play Pink Panther. My f***ing brain cells! According to their manual, it is better to stand like 10 feet away. Who knew? Let's run a single tone with a lamp on. This is loud. See, like I said in my previous video, the output power is interrupted at a certain frequency which I can tune using this interrupter. It's like punching air at audio frequency which makes this sound. Playing music might be better. Why does it feel different? It feels like an actual painful electrical shock, unlike my old Tesla coil. If you remember my old one, when I touched it directly, it would just burn my skin. Or if I touch it with a metal rod, I wouldn't feel anything. This is different. I like to measure the output waveform of the Tesla coil, and for that I created a single loop on my probe that will pick up the electromagnetic energy radiated into air by the Tesla coil, and the oscilloscope will show it. Also, I have a ground rod here that the arc will jump to, and hopefully not to my scope. Let's try it. See, we have pulses of energy. So what we captured is that at 1 kHz setting we have a pulse every 1 millisecond, and the pulse duration at maximum setting is around 40 microseconds, and the resonance frequency is around 300 kHz. So that's why this arc hurts like shit. See, in my old Tesla coil I had a continuous stream of 1 MHz signal which would not penetrate inside the body due to conductor skin effect. Look it up. The skin effect is when the flow of electrons is pushed to the outer skin of the conductor due to the electromagnetic fields generated by AC current. The higher the frequency, the thinner that outer skin becomes. This thing pulses energy at frequencies lower than 1 kHz, which means it has strong low frequency harmonics that will penetrate deep inside the body and is definitely harmful. So never try to touch this at home. I'll give away 4 of these at the end of the video so you can exercise not touching it at home. Let's try touching it one more time for science. Let's use a rod. Using this rod at lower frequency, I can still feel it tingling my muscles and nerves, but it's much less painful because the electricity is distributed over a much larger surface. Let's see if it can turn on a lighter. I need a Faraday cage. Well, the Faraday cage is a metal cage that encloses the body completely. This is just a metal foil mostly open that I'll connect to ground so that the arcs jump to it rather than going through my body. Okay, here we are, my metal glove connected to ground. There we go. Yeah! There we go. Now I'm wondering if my spinning wheelie thingy will work on that, so I bent this wire in shape and I'll place it on Tesla coil. Okay, let's balance it on. Of course, I expect it to turn much slower than mine because in my Tesla coil I had a continuous power output, but this is a much lower duty cycle arc. Let's try it. Oh yeah, going. Let's instead play some music. Okay, let's get back to the circuit and try to understand how it works. First, the Tesla coil itself, which is the heart of well, Tesla coil. It's just a transformer made of a primary with a few turns of winding and a secondary with 1500 turns in case of this OneTesla kit. The secondary of the Tesla coil is just an inductor connected to a capacitor and they resonate. That's all. There is no magic. It doesn't pick up any strange energies out of nowhere. Tesla never tapped into free energy using his coil. There are millions of engineers every day that use inductors and capacitors in all sort of shape and form, and none of them ever pick up a free energy out of nowhere. Ever. And that's final. Now that that's out of my system, let me show you how it works. Like I said, the secondary is an inductor that is placed in parallel with a capacitor. And that capacitor is made by this toroid or top load to the environment. And the bigger the top load, the bigger the capacitance. An inductor and capacitor connected together will oscillate if they are charged. It's like connecting a weight to a spring. If you pull the weight down, you will charge the spring. If you let go, the spring will pull up the weight, loses its own energy, but stores it in the weight in the shape of kinetic energy. So now the weight will start contracting the spring and loses its kinetic energy and stores it in the spring. And then the spring pushes the weight back down again. So this oscillation continues going until the system loses all its energy due to friction. Same goes for a capacitor and inductor. Try to remember this. A capacitor resists against change of voltage across it, but an inductor resists against change of current through it. So for example, if I charge the capacitor to a voltage like VC and connect it across an inductor with zero current, what happens is that initially the inductor doesn't want to change its current, so it stays at zero. But as the capacitor continues pushing energy into the inductor, its current rises to some level as it's charging, and at the same time the capacitor voltage drops all the way to zero because it's losing energy. Now we have a capacitor that doesn't have any energy, but the inductor has charged to some current and wants to continue pushing it through into the capacitor, so it charges the capacitor backwards. The voltage of the capacitor goes all the way negative and the current of the inductor drops all the way to zero. Again, we have a capacitor that's charged and an inductor that doesn't have any current. The capacitor pushes its energy into the inductor and the inductor charges to some current. So this continues going for a while until the system loses its energy to the resistances of the circuit and radiation. The oscillation frequency of this circuit is 1 over 2 pi square root of L times C, which is the inductance and capacitance values. This is also the resonance frequency of this circuit. Now anything in the world can store a lot of energy at its resonance. You just have to excite them correctly. So if I hit this inductor and capacitor at resonance frequency, it will build energy upon energy and the voltage will be so high that the arcs will jump out of it like you saw. Now how do we transfer energy to the secondary? By making a simple transformer, winding a few turns of primary and then provide an AC with a frequency that matches the resonance of the secondary, and that is guaranteed to keep the excitement going. What do we have here? A low power full bridge rectifier. And here's a cute little transformer. Like a traditional wall adapter, first they have a transformer that steps down 120 volt AC into 12 volt AC, which has 17 volt peaks. Then they feed that into a full bridge rectifier and a capacitor that generates around 16 volt DC. Then they feed that 16 volt into 15 volt and 5 volt regulators to power the low power circuit. Most solders come with something called the flux. What it does is that it cleans the surfaces to be soldered from oxidized layers so the soldering can be done much easier. But then the flux creates these fumes that's, I suppose, not very good for health. There are these fans you can buy that sucks the fumes away. It's time to mount the power IGBTs on the heatsink. IGBT is a type of transistor that's a mixture of FETs and BJTs. You don't need to worry about that though. It's like a switch that opens and closes based on the input signal. These things heat up quite a lot. That's why they have to be on a heatsink to cool down. Our IGBT switches are arranged like this between a positive and a negative voltage supply, and their output here goes to drive the primary of the Tesla coil. They open and close one at a time and connect the voltage here high and low and create a square wave. Now this is an interesting transformer. It drives the power transistors. This part is a bit complicated to explain. I'm just gonna say, if you think you may get brain cancer, just skip forward. Here are the IGBTs. They require a positive voltage between gate and emitter to turn on. But you can see here that the emitter is connected to a minus 170 volt DC, and this emitter is switching high and low as so you can't drive this directly from your low power circuit. So they are using a 1-to-1 transformer like this with one primary and two secondaries. The secondaries are isolated so they can be at any voltage they want. Now they provide an on-off signal to the primary, which is repeated on the secondaries. One of the secondaries is connected backwards so that when one of the switches is on, the other one is off. Otherwise, if both switches are on at the same time, it will short the power supply and boom! Okay, so far so good. Time to check the low power circuit. Okay, let's power it up. According to them, I should... It's definitely beneficial to check the direction of your components before powering it up. Fortunately, I think I have a replacement. There, it's good now. And this thing wasn't wire. It's an optical fiber that goes between the interrupter and the Tesla coil driver. The interrupter generates pulses with a certain frequency that turns the output power on and off, both to generate sound and to limit the output power so that the circuit won't overheat and blow up. It is connected to the driver circuit with optical fiber, which is not electrically conductive, so all the noise and radiations from the output won't go back to mess with the interrupter circuit, and also the user won't receive a shock, unfortunately. You know, I went ahead and got one of these fans. It's only $28 from Circuit Specialists. I recommend having it. It sucks the solder fumes away from your lungs and absorbs some of it too. I leave the link in the description if you want one. And now it's time to install the power full bridge rectifier. Now here's another awesome usage of the full bridge rectifier. Originally we have our ground connected here and AC comes here, and if we measure the output there, we get bumps like this. And if we put a capacitor at the output, we get a rectified DC. Now if we move our reference ground from here to here and measure this point, we will get positive bumps like this. And if we measure this point, we will get negative bumps like this. And if we put capacitors between these points and the reference ground, we will have a positive DC supply and a negative DC supply here. In the OneTesla design, they provide 120 volt AC here, which has 170 volt peaks. So we will have positive 170 volt DC there and negative 170 volt DC there. Of course, we don't need these two diodes and can do the same thing with two single diodes, but whatever. Isn't the full bridge rectifier just beautiful? Like I said, it's not a puny single diode rectifier. You can get this shirt from the link below as a tribute to our hero, the full bridge rectifier. Now this is interesting. The primary winding of the Tesla coil is made of thick white copper on both sides of the PCB itself. I think it's 7 turns if I'm not wrong. This giant capacitor is not directional and it's placed in series with the primary of the Tesla coil. Now this is interesting. We already know that we can have a square wave of plus minus 170 volt across the primary of the Tesla coil. But why stop there when we can add a capacitor right here, which with the inductor will have its own resonance frequency. If the frequency of this square wave matches that resonance, here we will have voltages in orders of thousands of volts, which will translate into millions of volts on the output of the Tesla coil. But the secondary of the Tesla coil already has its own resonance frequency, so the primary L and C must be designed carefully to provide the same resonance frequency as the secondary. This thing is a current transformer. The current that runs through the primary of the Tesla coil is sensed by this current sensor transformer. In OneTesla circuit, we are sampling the current of the Tesla coil's primary and feed it back to the circuit to make it oscillate, which oscillates at the same resonance frequency of the primary. This circuit doesn't have a feedback from secondary, unlike circuits such as Slayer exciter. So similar to the traditional arc Tesla coils, the designer of such circuit has to make sure that the primary resonance frequency exactly matches the secondary resonance frequency. But this also means if the environment around the Tesla coil changes, it changes the capacitance of the top load, changes the resonance frequency, and so the output power. See, like this. Have to apply a few coats of varnish to the secondary. We have huge arcs jumping from the top load, which I'm guessing are around 500,000 volt, if not higher. And this tower is around 20 centimeters, which means we have 25 kilovolts across every centimeter of this tower. That voltage is high enough to easily break through the wire coating and arc to itself, like I've seen in my old Tesla coil. This is why we cover the secondary in a thick layer of varnish to prevent unwanted arcing. And also this is why we wind the secondary in a single continuous layer from top to bottom. Because otherwise, if we overlap the wires, we are placing huge voltages side by side that will arc through and burn the winding. And this is most of the things you need to know about Tesla coil.
Giveaway time!
So, as I promised, thanks to OneTesla, I'll give away 4 of these OneTesla kits. 2 to my patrons at patreon.com and 2 to you, the viewers. Just let me know in the comments if you need one. Give me the OneTesla! And if you want to purchase your own OneTesla or Tiny Tesla kit, use the promotion code ElectroBOOM10 to get 10% off at OneTesla.com. And no, ElectroBOOM 100 doesn't give you 100% off. Although, give it a try, you never know who wrote the code.